Great. So this session is going to be recorded, and it's the topic of discussion today is breathing walls. For those that are new to Localtalks, Localtalks is a series of quarterly events about green design. There are talks about green design, and the aim behind it is to create an open forum for the exchange of ideas around the topic of green design. We've had quite a number of Localtalks which have been recorded and are available for you to watch on our YouTube channel. We have covered a range of topics, and you're welcome to watch, subscribe, and follow us on that platform. My name is James Musasizi, and I am a graduate architect working at Localworks, the entity which is behind these Localtalks, and I will be hosting this session today. Just a few things for us to note. This event is being recorded. We started at 6 and shall end at 8 p.m. So usually what we do is we have 30 minutes, as is the case today, for each speaker, because we have 2 speakers. But usually when we have 3 speakers, it's 20 minutes, then a round of questions and answers, and then we have closing remarks. Just to remind all of us that you can keep slotting in your questions in the chat box as the conversation goes on. The topic of today is breathing walls, creating healthy indoor environments in a tropical climate. We're going to have a 2-part discussion, which will be led by different speakers. Philip Murungi, a structural engineer working at Localworks. I will introduce him in more detail later. And Bernhard Lembeck, who is the CEO of ProNature South Africa. We are going to have an introduction to this subject by Felix Holland, who I am handing over to give us an introduction, after which I will introduce the speakers.
Thank you, James, and good evening, everyone. I'm not going to talk a lot, but I just want to say a few words why we picked this particular topic. For those of you who are not quite clear what breathing walls actually means and what we're talking about, I remember when I was in university studying architecture, we used to have a structural engineering teacher, and he always mocked us for talking about breathing walls. He said he has never seen a wall that breathes. But obviously, what we are really talking about here is, and that's sort of in the subtitle of today's session, it is about creating healthy indoor environments. And one of the aspects of creating healthy indoor environments is having good air quality inside. And how do you achieve that? We, and when I say we, I now mean sort of the designers in this part of the world, are fortunate to live in a relatively moderate climate. Certainly Uganda has a very, very moderate climate with outdoor temperatures that hardly change throughout the year. So things like insulation and mechanical cooling, so mechanical heating or mechanical cooling, all these things is something that we don't really need to bother with. So we are really in a very luxurious position where we can build the walls we like. And what are the walls we like? Walls that we like are a bit like the human skin. They are very good at balancing. They're very good at balancing out differences between indoor and outdoor. So you may find a certain condition where maybe on one side of a wall, the climate is a lot more humid than on the other. Now we like walls that are able to moderate between these 2 different conditions and ideally actually balance them out. And I think today we will see and hear about a few examples of how this can be achieved. It's quite obvious that if you had the choice of living in such an environment versus one where you're almost in a vacuum, almost packed into plastic, like what is now very commonly done in Europe, where of course everybody tries to build energy efficient buildings. If you had the choice, I think you wouldn't think twice. And I'm looking forward to hearing tonight a bit more of the background of how this is achieved, both in terms of the material, the structure behind these walls, and then also about the finishes of such walls, which I think Bernhard will especially talk about. That's all I have to say. I wish everybody a really interesting session, and look forward to the discussion at the end. Thank you.
Thank you, Felix. So the first speaker is Philip Murungi, who is the head of design development at Aquila Gallery, which is a member of Localworks. He is an experienced structural engineer with over 7 years experience in the construction industry. He is skilled in structural modeling, analysis, design, and drafting of a variety of building types. So Philip, over to you. Really excited to hear what you have to say.
Thank you, James. I hope you can hear me loud and clear. So let me go straight into the presentation mode. I hope. Can you hear me now, James?
Yes, we can. It's just a bit muffled. If there's something you could do about that, that would be great.
Can you hear me now clearly?
Yes, great.
Oh, much better.
Okay. Sorry, I think I just got in a bit unplugged. Yeah, so I hope you can see my presentation. Today I am going to be talking about breathable walls. It's probably going to be with a lot of science, but then at the end I want to show some applications of what we've tried to do here at Localworks and what that looks like. I'm basically going to focus on 3 things. What are breathable walls? Why is it important? Yeah, and what's the science behind it all? Okay, so what are breathable walls? Basically, breathable walls are simply walls that have the ability to absorb and desorb humidity. That is, to take in humidity or vapor from the air and basically to give it back. So all this depends on something called the equilibrium humidity, which is the maximum humidity that a dry material can absorb, right? So there are different breathable materials. We have timber is breathable, concrete is breathable, rammed earth is breathable, earth bricks are breathable. So, but before we get into all that, why do we really care, you know? Why is this important to us? So everyone lives in a building, at least most people, except if you live outdoors, and you'll find you spend a good portion of your time indoors. I saw research that said that in colder climates, people spend 90% of their time indoors. So the things that govern the comfort indoors become important. You know, the temperature of the room, the movement of air in and out of the room, the humidity, you know, the radiation. That's basically the heat being given off different surfaces, and air quality. Some things are felt more immediately than others. For example, heat, you feel the heat as soon as you get into a room. But there are others which control comfort, which are a bit more subtle, especially to those who are not experienced with building. And humidity is one of these. So before we see how walls are able to breathe, let's just look at the effect that humidity has on your health, right? So every human being has a trachea, which is a tube connecting the nose and the lungs, right? And when this tube is moist or has a good humidity, then it's able to prevent foreign bodies getting into your lungs. It has a sort of wave-like motion, which is the mucous membrane of what is called epithelial tissue. I hope I'm not boring you with the science. So basically this tissue has a wave-like motion where it returns things, foreign bodies, dust that get trapped in the trachea, right? And if the humidity drops below 40%, well, this tissue in the trachea dries out and it disturbs the movement. So the system basically fails to work. And now foreign bodies are able to reach your lungs. On the converse, if the humidity goes higher than 70%, right, then there are other effects you will feel. You will have reduced oxygen intake in the blood. You will have rheumatic pains if you live in a cold place. Fungal formation in rooms, fungal buildup is much higher, you know, when humidity rises above 70 or 80%, and there are even more spores. So what you basically want is a humidity that's between 40 and 70%, you know. So this kind of humidity in the room, it reduces the fine dust content in the air. It activates the protection mechanisms of the skin against microbes. It reduces the life of many bacteria and viruses, and it reduces the odor and the static charge on the surfaces of objects in the room. So then, what is the science? So having seen how this is why we care, see how it affects our breathing and all that. So what is the science then behind these breathable walls? So the science, to take you back a bit to your A-level physics or your O-level chemistry, is basically based on Boyle's law. I hope everyone who's done ordinary level physics knows Boyle's law. But it's basically, it says that the relationship between pressure, volume, and the temperature of a gas are constant, right? And if you look at this graph that I have shown you there, it will explain that if I am in a room in a country that has a cold climate, and the air outside is at 0 degrees Celsius, and it has a 60% relative humidity, that means the amount of vapor, you know, it's not yet fully saturated. And so this cold air comes into the room. And because my room is being heated to room temperature, it's about 20 degrees Celsius, if you see on the graph. So what happens is that as the air coming in is heated, it loses humidity. So the humidity decreases to less than 20%, right? So, and even if you look still at the graph at the blue arrow, even if the humidity was at 100% at 0 degrees, and it came into a room that was still at room temperature, it still would drop from 100 to less than 30%. So in both cases, it becomes necessary then to raise the humidity as soon as possible in order to, you know, maintain a healthy and a comfortable condition inside the room. And the question we want to ask today is, how can this be done, you know? How can we regulate humidity inside the room? And the way people have done this over the years, I think the last 40 years, is we use the furniture, we use the ceilings, we use the floors, and also we use the walls. And today I'll be talking about how walls do this. So research has been done in Germany at BRL, is mostly in the 80s, 70s, and actually the 80s, quite a while back. And so here, sorry, more curves. We're looking at how porous materials are able to absorb and desorb humidity from the ambient air. And basically what they did is that they got samples 15 millimeters thick, that's 1.5 centimeters, at a temperature of 21 degrees. And then they caused a sudden increase of humidity from 50% to 80%. Again, if you know Boyle's law, basically, if you keep the temperature constant, you just vary the pressure, and then the volume of the gas will change, right? So what they found when they did this, and what the first graph will show you, is that the 15 millimeter thick layer of a mud brick wall is able to absorb about 300 grams of water per square meter of wall surface in the first 48 hours. And that's, if you look at the first graph, that's the curve labeled 1. No, sorry, not the first graph. If you look at the second graph, that's the curve labeled 1, right? That's mud brick. And this is after a rise from 50% to 80%. And then if you compare with, say, lime sandstone and pine wood of the same thickness, it only absorbs about 100 grams per square meter. And then when you have ordinary cement plaster, it's 26, varying between 26 and 76 grams per square meter. And then baked brick, which is your new usual fired clay brick, is only 6 to 30 grams in the same period of time, right? So you would see that the mud brick is able to create a balance in the humidity much faster than these other materials. So now let's take this observation and now spread it over 16 days, and you can see what the effect looks like, right? So basically, at this graph, you can see different materials, and in the brackets, you can see their densities. And you see where concrete is, your class 15 concrete, right at the bottom, you know? And then your normal cement concrete, 220, those are cement blocks, also right at the bottom. And then your porous bricks, and it keeps going. We keep getting better until we come to earth, so earth being the best. But you can see between earth and your clays, by mixing in different, mixing straw into the earth, you're able to get well, much better behavior than bricks, but still not quite as earth right at the top. Yeah. So now, again, another thing we have to think of is the effect of the thickness of the layer of the earth on these absorption rates. And when you look at these graphs, what it shows you is that in the first 24 hours, only 2 centimeters of the earth is effective. So they tested both 2 centimeters thick, 4 centimeters thick, and 8 centimeters thick. And over the first 24 hours, they had the same behavior, right? So again, the bottom axis shows the time, which is in days, and the top axis shows the absorption and desorption rate. So then after another, say, after 4 days, then 4 centimeters and the 8 centimeters, which is 40 millimeters and 80 millimeters, they behave the same. So only if you have an 80 millimeter thick layer, after 1 day, only 20 millimeters is effective. After 4 days, only 40 millimeters of that, only half of that is effective. So it's over only a larger period of time that then a larger thickness becomes effective. And so many times this begs the question, then why do people have bigger earth walls? And that's simply because of strength, you know, because earth, you have strength below usually 10 megapascals, so 5, usually even 2 megapascals. And when you compare that with concrete you have for class 25 about 25 megapascals. So you need a much more considerable thickness to achieve the same effect of strength. But of course, today we're talking simply about breathing. So then the other thing we would look about is when we coat this. So what happens when you apply a coating on top of, say, earth? And when you look at this curve, you will see that at curve M is simply our earth with no coatings. And then as we begin to add coatings, the effect, the breathability of the wall begins to drop. So each coating here is about 100 microns thick. And it's the same humidity rise from 50% to 80%. And the wall is 15 millimeters thick in total. And what you'll see is that your acrylic paints, well, they lower the ability of your wall to breathe, basically. Your synthetic paints do the same. Your latex substances do the same. Your primers do the same. The materials which don't have such a pronounced effect, maybe your linseed oil is not so bad. Linseed oil is actually bad, sorry. As maybe your limes. So lime is good, and lime plasters are good. And here is just an example of a wall we've done in Luengo district. And it's the infill blocks are a mixture of earth and sawdust. And then we coated them with lime earth plaster. And another thing also to think about is when you add maybe something to the lime, what is the effect of this? And so this previous example we've looked at where we had the lime earth blocks with sawdust, it's your curve L1. And it makes the walls much more breathable than ordinary loam, so ordinary earth, which has no fibers. And when you look again at this graph, what you will see is that straw materials, your fibers, improve the breathability of earth, whereas lime and cellulose glue or rye flour, when mixed in, they don't do much for you. They actually basically lower it. So now let me just look at some applications of what we've done. And this here, this picture is a earthbag wall we built in, where is the place? I forget the place. It's at Mustard Seed Junior School. And it's basically rammed earth, which is in bags of sacks. We ram it together, then we fill in the infills, we smoothen them out with cob, and then we apply 3 quarts of plaster, which is your earth plasters and lime mixed in plasters. And the last example I wanted to show is a video. Let me just share screen, advanced video. Let me just quickly share. I hope, can you see I hope you can see my screen. So these are these are timber frames we're building in Luengo district, and the infill earth blocks where basically we're mixing sawdust, cement, and earth, and we're basically compressing them under pressure, creating these blocks. So this is the pressing machine, and they're basically marked, with depths to show what amount of material to put in. And the mix is about 1:1:6, lime, cement, and sawdust. The sawdust basically increases the breathability of the wall. And here they use a jack, basically to create some hydraulic pressure and ram it down. Yeah. And this guy should have known that a longer lever would have worked better than, stepping on it. So then they remove these earth blocks from the mold, and they take them and place them on the side to cure them. Yep, there he goes, checking the thickness, quality control. Yeah, and when both sides are even, when he's sure both sides are even, he just places them to cure. Yeah, and now these are the cured blocks placed in the timber frames. And now we coat them with a plaster. The mix we use is about 1:3:12, which is cement, lime, and sand. Still breathable. One of the breathable coatings we use. So that the mixing pit inside the house. And so here, this is the lime in the wheelbarrow. It's quite caustic, so you need gloves to handle it. It irritates the skin and actually causes it to peel off. Yep. And there they're applying the substrate to the walls. They apply it in 3 coats, a scratch coat, a second layer, and then a final finish. So that's the scratch coat when they're applying it. And yeah, that's the guy mixing. Yep, and there's our mason. Yeah, and that's the last coat. And on top of that, then we put some earth finishes, basically pigmented earth, well, pigmented plaster, sorry, was the final coat. And if you saw, those were samples, and we had even written the mix on one of them before we get, of course, the architect to approve the color. Yeah, so I think that's it from me. Thank you. Let me hand you back to James.
Right. Thank you very much, Philip. very informative. I would like to remind everyone that has tuned in to send in their questions. I notice in the question and answer chat box, there's nothing yet, but do send in your questions. The next speaker is Bernhard Lembeck, who is the CEO of ProNature South Africa and is known as the Green Chemist. Bernhard follows his calling to develop and make available the most sustainable coatings, technology in wood furnishings, and architectural paints. Without further ado, I will hand you to Bernhard.
Good afternoon, everyone, and thanks so much for letting us participate in this thing. Philip, a wonderful presentation. You stole half my thunder, but I will be going into a little bit more detail on all the things. So let me share my screen. If there we go. And then we can get into the presentation. My apologies, it's a little slow. James, is that visible?
Yes, it is.
All right, okay, cool. So I will be reflecting predominantly on breathable coatings, which is supposed to go hand in hand with the breathable walls that Philip was so elaborate talking about. And you will probably see some duplication of what he has said, but these things go very much hand in hand. And I must congratulate the development in Uganda. We failed to see where we have done similar things in South Africa, and we are involved with a lot of environmental projects, as you can imagine, in what we do. But this looks amazing. I like this semi-industrial making of bricks and floors. It's wonderful. All right, let me start with my presentation, and that will surmise into trying to explain the significance of permeable or breathable paints. What are the major compositions? What are building and substrate requirements? And why ventilation is so important. And ventilation, Philip has mentioned quite a bit, but nevertheless, we will go ahead. So let's get going. I mean, when I researched that subject a little bit more in detail in order to prepare myself for this presentation, I found two opinions, and but in summary, one can say that these breathable substrates are very much enjoyed in conjunction with breathable, or rather the other way around, sorry, that breathable substrates enjoy breathable coatings. And if you look at the Northern Hemisphere, where they try to painstakingly not to lose any energy in buildings, breathable coatings are not really the ideal scenarios. So they believe we rather shut off the walls and we don't bother about room climate and so forth. I believe, or we believe, that is in general it's advisable that also allowed to release it again. Often the case is that in substrates where we have these combinations of clay, lime, straw, and other natural fibers, that they are coated with non-breathable coatings, and which doesn't allow the moisture that is trapped within those walls to evaporate again. And as much as you have sorry, I lost myself here. Apart from sound textural features like sufficient groove overhangs and good ventilation, it is always advisable to protect such structures from water, maybe that of the rising or raining kind. However, should moisture have accumulated in or affected such structures, it is vital to allow such moisture to dissipate and not to be trapped behind an impenetrable paintful. And that's where permeable or breathable coatings are called for. Breathable coatings in general are suitable to release moisture from moist substrates, which will protect the substrate, but main moisture removal cannot be through the actual coating, but through proper ventilation. I think that is very often overlooked. So what are these breathable coatings? Sorry, I went one too fast. A breathable coating can either be a coating which allows moisture transfer from the substrate to the outside, but prevents the ingress from rain on the other hand, or be a coating that becomes part of the substrate, like the so-called silicate-based coatings. Coatings which allow moisture transfer either by one or bidirectional are called breathable or permeable coatings. The permeability or breathability, also called moisture vapor transmission rate, also water vapor transmission rate, my apologies, is a measure of the passage of water vapor through a substance. It is a measure of the permeability of materials and substrates. There are various test methods around on how to establish those figures. And I found quite an interesting little scale where they actually try to demonstrate the water vapor transmission rate on paper board, which is probably easier to measure than a whole wall. And the paper board actually allowed a absorption of 850 grams per square meters in 24 hours. And by coating that paper board, in this particular case, we didn't do those studies ourselves. I just present a copy thereof. They used tall oil fatty acids and coated that in various forms and concentrations. And one can see how a coating can actually stop that absorption of water into a substrate quite substantially. That is something that we as paint chemists don't really want, so not so much the absorption, but if there's absorption, we would love it to be released again. And so let's have a look at the main breathable coatings and what is available and what they are based on. A typical type of permeable coating can be based on natural polymers like linseed oil. And Philip, I was rather disappointed that you mentioned linseed oil as not being a good polymer to use, but we like to think otherwise, because we know that in the correct formulation, the correct presentation, that linseed oil indeed actually, like I said, if formulated correctly, allows very much for a breathable coating. But the and on the other hand, also it allows also to protect the walls from the ingress of water. So obviously you don't want to have a earth-based paint or coat wall plastered with the formulation that you presented to be rained on for any length of time, and then the whole building to collapse, or at least the plaster to fall off. Then the other group that I mentioned a little bit earlier already are the silicate-based coatings, which can actually chemically react with the substrate. So they're not really forming a film as such, but they are indeed very well known to allow for the release of moisture, and by adding various additives to the silicone coatings, we can also avoid the ingress of water. These silicate coatings, unfortunately, preferably require a substrate that does contain some silica in one form or other, and that's where they best perform. A further coating type with a high water permeability are lime paints, which are well known in Africa. I mean, they're used everywhere. However, they require fairly regular recoating, especially on exterior applications, and are not really suitable for very rain-prone areas. But they are nice and cheap, and that's what makes them rather attractive for the less affluent markets. So if we look at a little bit of the summary and look at the permeability of various coatings, we find that the distempers, which in fact would be yet again potentially a plant oil like linseed oil, combined with various fillers and so forth, the lime casein paints that were mentioned already, and the dispersion silicate paints, and potentially matte dispersion paints, whilst the latter really show the least of the high water permeability. Glossy mulch paints and insulating paints and acrylic paints, for example, are moderately permeable to water vapor. And in the third group, the alkyl resin paints, which are your traditional enamels for timber coatings, so forth, 2K epoxy resin coatings, 2K pure polyurethane paints, my apologies, have a very low water vapor permeability. Let's have a look at a little test that we did here in the lab for this presentation. We coated a cloth with, on the one hand, with acrylic PVA, and on the other hand with our, and believe it or not, in part containing linseed oil, our own coating, which we call ProNature Wall and Ceiling. And we strapped this cloth that had been curing for a number of days, that we have a proper dry paint film. We strapped this over a beaker on a hot plate and just boiled the water underneath, and wanted to see which coating is more permeable than the other. And if we have a look at the acrylic PVA, and that was happily boiling and nothing really happened. And in the end of the exercise, the steam actually came out of the side from underneath the cloth through that strap, and it had to go find a way out of that beaker. And if we look on the other hand at a coating that is based on predominantly linseed oil in combination with lime and casein, you will see that after a certain boiling time, that the steam actually comes out through the cloth on top. And just to demonstrate that differences in polymers can very well make a huge difference in terms of allowing for a breathable wall. All right, but just looking at coatings is probably not quite cutting the thing. What we prefer to see, especially on buildings that have utilized natural building materials, we like to see large roof overhangs, which is in South Africa hardly ever the case, and we even in conventionally built buildings see the detrimental effects of the weather, whether it's now from sun bleaching or wind and rain. They're rather detrimental, especially in these very fast developed settlements. Proper drainage of rain and surface water, which I could imagine in the buildings that Philip reflected upon, is also very important. A non-leaking roof. It might sound funny, but it is quite often that where a roof has a leak, that there is substantial damage in the within the building, because the water gets trapped direct on top of the wall and seep right through. Some breathable coatings may need to have a certain substrate composition, like I mentioned earlier for the silicate coatings, that they require some silica within the plaster or wall composition to chemically react with the substrate. Substrates should always have a reasonable integrity. Friable surfaces are not the favorite substrate which paint chemists have to deal with these days. And why is ventilation so important? I think that was missing a bit. I think ventilation is important to protect the substrates, to avoid that deterioration, which I had shown a little bit earlier on the slides, a previous slide. The prevention of mold and the inherent health implication, which were already reflected upon, to avoid pulmonary problems and allergies. On a further point, what are the implications of higher moisture buildup in buildings? It can be the destruction of the substrates. You know, if there's too much water in the wall, that is never appreciated. Baked clay bricks may weaken. We have this particularly here in Cape Town, in certain areas where we have a high groundwater table, and old buildings in part are showing bricks in close to the foundations, where you can literally poke the brick with your finger. That's how soft they have become. Efflorescence is certainly a problem in bricked buildings, which probably is something that in a clay building would never be a problem. Air-dry bricks are crumbling. Plaster failures like delaminations or paint delamination, which is always a problem, and mold manifestation. And if you look at these examples, Felix was mentioning the situation in Europe where they try to encapsulate the building, and with lots of insulation, there's hardly any air exchange within the building, and mold is a huge problem in Europe, but also down here in Cape Town, where we got very high humidity winters with cold weather, and mold generally is a problem. And what is the problem? Missing ventilation. So I reflected on crumbling plaster, the efflorescence, and paint that simply peels off because there is too much moisture trapped behind the paint film, and those paints were not designed to allow for a release of the moisture that is trapped within the wall. So from left to right, we see another wall with efflorescence, and you can see at the bottom here, there's a whole brick missing, which is simply disintegrated over the years. On the right-hand side, these are earth compressed blocks for a project here in Cape Town, which I actually visited only 2 days ago, where they sought our advice on how to repair those bricks, which is going to be a lot of fun. It's a massive school hall, and they had a leaky roof. That's where the problem started. All over, right around, it's a massive building, and most of the walls look very similar to that photo that I put in here, and that was just caused by the ingress of water. These earth blocks, which had just a minimum amount of cement adhered. I mean, they lasted for, I think the school was built in 2002 or something, so they lasted for a very long time until that roof gave problems, and yeah, it looks like a very sad affair. So I mean, a breathable coating, I think in this particular case, wouldn't even have helped. All right, so a few tips, I'm sure you as architects will all know what they are. Keep your building materials dry. That was not so much for the building methods that Philip was reflecting on. On roofs, provide a clear path for the water to exit. Yet again, a big problem in very modern building designs with lots of flat roofs. There's blocked drainages, and they're generally a nightmare so far as I'm concerned. Sufficient waterproofing behind shower installations. That is a huge issue literally in all the fast rising new developments here in Cape Town, because that waterproofing is either insufficient or simply missing. Install your wallboards and drywalling only after the building is fully enclosed, so that requires some solid project management, because we often see that the windows and doors are not in and the drywalls are already up. Ventilate during construction, very important, and then dry your concrete floors and streets before they are covered with other wall-to-wall flooring and tiles, whatever the case may be. Another important point, air-conditioned roofs need to be balanced for even temperature to avoid condensation. In some of the office complexes in Cape Town, which are really sealed very properly to avoid the cool air to go out again, there is often a problem that there is plenty of condensation on the inner walls and sometimes even on the outer walls. Further problems that we quite often come across and that a breathable coating won't fix is direct near foundation irrigation away from the building. Provide sufficient damp-proof cores, often a thing overlooked or done insufficiently. And maintenance, it doesn't help if the gut is not blocked and drains are blocked and the house gets flooded or the walls are in permanent wetness or wet feet, so to say. And ventilation, again, is my favorite subject for increased airflow. Seal the water sources like showers and so forth, and ventilate. Reduce humidity, not to a degree that does affect your health that Philip was referring to, but super high humidity will also not be of help within buildings. So an extractor fan in the bathroom might be quite valuable. That is pretty much it from my side. I just quickly slotted a last slide in there whilst we were still having our dry run earlier. And I think bottom line is that it is a fallacy to believe that a breathable coating will cure the sins of bad planning and bad ventilation, but it will certainly assist to keep a well-planned house dry. And yeah, if you enjoy more information on our coatings, please come and visit our website at pronature.co.za. That will give a lot more information on some of the coatings that we do, and certainly some of the coatings that were mentioned in that presentation. And yeah, thank you for your attention. My colleague once created a little summary of a breathable coat kind of thing in one short essay. So that is fleshed in here. So if you enjoy it, download it, and yeah, all from it from our side. And thanks again for having us. And James, back to you.
Thank you. Thank you very much, Bernhard. It's been a very interesting and informative presentation. Some of the things that I was noting were the fact that Philip went to a great depth to speak about the breathable substrate, and you have hinted on the fact that these two work together. You need a breathable substrate and then a breathable coating, which sort of brings me to my first question, that if at all you have these different, the substrate and the coating dissolve at a different rate, do I run the risk of trapping moisture on its way out of the room within the substrate because of maybe it dissolves slower? For example, baked clay bricks, which we use a lot of here. So if at all I have a lime-based plaster internally on my baked clay bricks, is there a chance of the moisture getting trapped on its way out? I think this is to Philip, because you also mentioned something around the effectiveness of the thickness of a material, and you showed 20 millimeters. So maybe throwing some more light on that, how the different rates of desorption in a wall buildup affect how quickly that moisture gets out of the room.
That's an interesting question, and of course, it depends on the difference, on the difference of absorption and desorption between these two materials. Your specific example of brick and lime is even more interesting because there's a project recently we're working on, and you have these walls which have been basically compromised by rising damp, and we've opened up the foundation and we wanted to basically protect them. So we can't put in a DPC to prevent the water going higher. But so we're thinking, how can we prevent water getting in from the sides? And what we use is a lime plaster, because lime is that material that is hydrophilic, I would say. It loves water. It basically sucks the water out of the brick. And of course, if the rate is too high, then it would cause cracking. But the rate is not so high. It's a more slower, more natural process. But even in a few days, it sucks the water out. And then lime is also that material that when you mix it with cement, it's strong and you can form a coating which is breathable, which, like Felix said, is like a skin that it sweats. It allows humidity out, but it keeps water from getting in. But yeah, if you put paint on that brick, you will get problems that you will see, because the difference in the absorption rates is so high. Whereas the difference in absorption rates between lime and brick is not high enough for you to see problems like that. I hope that answers your question.
Yes, it does. I have a couple of questions within the question and answer chat box. Trevor Atuhaire says, I was amused by the Luengo project. I liked its outcome. I'd like to know the durability of the structure given threats to timber like termites, moisture in earth, and heat? I think that's to you, Philip.
Okay, interesting question. He said termites, he said moisture and heat. So I'll tackle termites and moisture together. So termites and all insects are basically looking for food. There is a minimum moisture content at which timber becomes food. It's about between 14 and 20%. And anything below that, you're basically safe. So the first thing we do, of course, is to season the timber and keep the moisture content below 14%. And the next thing, of course, is to treat it, to basically denature it a little bit to prevent it from being food. And we use some more natural compounds, boric acid and borax, a mixture of the two, and basically we treat these, we soak them in it. And then the last thing we do is, of course, to seal it against, and Bernhard talked about linseed oil. It's a very good sealant. But also we have the plaster on the outside, basically prevent the insects from getting there. And then about the heat, you will find that lime plasters and the earth blocks are very good at regulating temperature. I think what most people are usually concerned about, in addition to insects, is the load on the structure. But you find that for centuries, people have been using timber to build. It's a very good material. And you also find that we coupled this with a steel portal frame. So just steel hollow sections. So it works pretty well. It's quite durable, I would say.
Great. Just requesting Bernhard, if you could kindly unshare. I see a hand from
sorry,
Felix.
yeah.
Yes. So Felix.
I just thought I could chip in with one further point that Philip didn't make. He generally explained exactly the strategy of these projects. In addition, you may have seen on these photos that we've actually raised up the entire building over the ground. So there is a concrete upstand. If you think of how buildings were built for centuries and how actually still in Uganda, many village houses work, they are built in wattle and daub. So there's a primary timber structure, there's a grid of bamboo or branches, and then there's natural earth plaster applied to them. Their weakness is, of course, normally where the primary timber structure touches the ground. They are normally just rammed into the ground or built around stone foundations, etc. So in this project that you've seen there, which is a fully prefabricated, we call it eco prefab. So it's kind of an ecological form of a prefabricated simple house. We've tried to address that by creating these little upstands, which of course help massively by not allowing direct transmission of humidity from the ground into the structure. Then they also create a fairly strong and long-lasting skirting, if you want, on the inside, and by just providing a bit of protection to the natural plasters above. Just to add that.
Okay, thank you. I have a question from Charles, who asks, what is the maintenance required for breathable walls? And how do you ensure they continue to function effectively over time? So I think for this one, maybe Bernhard, you would like to answer it.
Well, it often depends. I mean, we all know every building has got 4 sides, and in some areas it does require less maintenance. It's also very much dependent on the climatic condition. I don't know where that gentleman is based, but we generally look at maintenance intervals for further coatings within 3 to 5 years, depending on the environmental conditions that the coatings are under. One needs to highlight in this particular case, and maybe I should have reflected on that a little bit more in my own presentation, that even a breathable coating, if applied multiple times, will eventually lose their breathability, especially if they're polymer based. I mean, that doesn't go so much for the earth coatings that Philip was polymeric system, whether that is now a natural polymer or a synthetic polymer, it doesn't really matter. It's always a question of film thickness on how it allows for a breathability still. I mean, even a breathable coating, if I apply it 3-4 times, will eventually not become breathable anymore, because we like, like every little gap where water could dissipate, we put more polymer on top. So eventually that will be a solid film of a coating. We have, on the other hand, have had very good experience with either lightly or non pigmented coatings, or literally clear coatings, on some straw bale buildings in Stellenbosch that we did over 22 years ago. They were the first time coated, and predominantly because the house owner was sick and tired of seeing the clay colors. She wanted a colored and nicely colorful house, so we then changed that. But until then, it was just a clear coating on a straw bale house with a normal lime render on, that we applied that particular clear coating, and it performed extremely well. I don't generally give out guarantees for coatings, but we were very proud that we managed. I think it was about 14-15 years that the coating was on without any failure. But I mean, to be on the safe side, you probably look at about a 5-yearly routine maintenance.
Great.
What type of coating was that in specific that you then applied, when you mentioned sort of quite colorful coatings that you applied? What would it be based?
Actually, initially it was a combination of various plant oils, the main contender again being linseed oil. That is sort of our bread and butter polymer for all these natural paint manufacturers. And thereafter, we then when we went for the colorful coatings, we used our standard wall coating, which is still not quite as breathable, because it's so much filled with pigments and other extenders, where we use a linseed oil casein base, and that generally is known to be rather breathable, but not to the same degree as the clear coating.
Okay. A question from an anonymous attendee who says, besides enhanced breathability and the health benefits that this comes with, does this approach offer more enhanced opportunities in cost, durability, time, etc.? So my understanding of it is, how does it compare cost-wise with, just doing the regular, I guess, petroleum-based paints or other kinds of construction that may not be as breathable? Philip, you want to have a go at that?
Well, I guess if it comes to paint cost, I need to answer that.
Yeah.
In general, we are, in comparison to conventional PVAs, as we all know them, polyvinyl acrylate and so forth, conventional synthetic wall paints, we are found at the top range, kind of, there's a huge price gap or price range available in the markets, from dirt cheap to super expensive. We, unfortunately, using natural ingredients, you tend to be found more in, not quite on the super expensive side, but there certainly is a remarkable difference between a non-breathable and a breathable coating in general. You probably look at about 30 to 40% more expensive. But we believe that breathability, and also the fact that we are using sustainable raw materials and whatever else goes with making natural paints, certainly would be worth spending that kind of money. And it's also important that using breathable coating, especially in the scenario that Philip has pictured, certainly would be very beneficial for the building structure as such. You know, if you keep a clay-based structure permanently wet, we all know what happens to that. It will eventually collapse. The plaster will fall off the wall. So it's, I think, the disadvantage in price we can certainly make up with a lot more benefits for the building and for your health. Yes, obviously.
So I'll just add a bit, taking the case studies of what we worked on, because that's what I know more about. So anytime anyone says anything about climate friendly or sustainable, usually, yeah, it tends to be more expensive, right? But there are specific cases, you know, where things make more sense, and when sustainability is the obvious answer. If you go to a place and you want to build and you use the soil from there, you're cutting out transport costs, even the labor costs reduce. When we build with earth bags, this is something anyone at home can be taught to do. So the labor cost, yeah, goes down, and these are much more breathable than concrete, right? This project that we did in Luengo, it's prefab, it's much faster. Everything is done in the factory, that the panels, the frames. And so the only in situ things done on site are the concrete kickers, the infill blocks, but it takes a much shorter time. And when you compare it to what the solution we used to have before, which was fired clay brick of full brick thickness, it's cheaper in this specific instance. So everything depends on context and the circumstances, I would say.
To add one thought that I always would like everybody to consider who asks the cost question. The cost of what? As in the cost of the initial investment, or the cost over the lifetime of the building. And I really think we should all go away from looking at the initial cost. It's such a narrow and really undefendable way of looking at the cost of anything that you do in life. You need to look at the life cycle of this entire building. To give you one example, we have on a number of projects now just simply used earth pigmented lime plaster. Lime itself, the type of lime that we are using is more expensive than cement. So if you just compare the cementitious plaster with a lime-based plaster, and you spend more per square meter. But then, of course, we are using earth, sieved earth, as a little bit of pigmentation in these plasters. And of course, that we are getting on site practically for free, certainly for free as a material, and then there's just a labor component in it. The interesting thing with this stuff is that when you apply it, it creates sort of a slightly uneven finish, a kind of a hand-applied finish. And that over the years fares extremely well in terms of maintenance requirements. I noticed that when you start, living in these spaces and using these spaces, and maybe some fingerprints appear on the wall, etc., the need to repaint comes far, far later than in a wall that is perfectly painted and coated like, a normal chemical, paint. If you go to a typical Ugandan upcountry school that has cementitious plaster and normal, vinyl paint or whatever they use, basically after 1 week you just want to repaint that building because it looks so horrendous. It looks, the dirt comes from the floor, the splashback, the dust from the environment, etc., the fingerprints. Whereas with these natural plasters, you just don't have that feeling because they're far more forgiving, and therefore, I would say the life cycle costs only reduce.
Oh, very true.
Yeah, and just sorry, a small quick addition. So the lime can actually be got as a byproduct of different processes. So in places where steel is manufactured, it's a byproduct of the slag. In places where here, like we get it from, I think, Uganda oxygen, where it's this carbolic slurry, and it's really much cheaper than you would think. So, and when you look at all these, the cost effectiveness of it all tends to add up. Yeah.
Great. Namanya Guy asks, what are some of the challenges Localworks has faced while using some of these walling techniques, and how have they been overcome? he asks quite a number of questions. So I think maybe we go one by one, because by the time I finish them, we may need to be reminded of the first. So the first is, what are some of the challenges Localworks has faced while using some of these walling techniques, and how have they been overcome? Philip or Felix?
Should I start, or should Felix start? So let me start with, of course, one of the immediate challenges is strength, right? How to get the required strength to keep this thing standing, or to put some weight on it. And different materials have different breathability, true. But natural earth, when rammed, when compressed, has considerable strength. Then in Lwengo, what we used is timber. So by pairing two breathable materials, we're able to use their strengths. Timber is very good along the grain, so it has good tensile properties along the grain, and that is one of the solutions to strength. One of the other things I found is bias from people. Basically, you have to tell them, to explain to them that these materials have strength. The other thing they always say is termites, insects, durability. But like we've just been talking about, Felix said earlier, we've taken a number of measures to make sure that these buildings are sustainable. So I guess I would say those are the techniques we have used. Yeah, maybe Felix will add something.
Well, I think just a general challenge is that many of these materials and products that we're then trying to use are not available off the shelf. And I think that's a challenge. I'm very often asked whether the stuff that we are doing is scalable. Honestly, that was one of the reasons why we decided to invite Bernhard, because it is, of course, in Uganda, we do not have any paint manufacturer, for instance, who does these type of products where you can just go and buy them in tins, which you can do, of course, if you are in Cape Town. So here it is all about kind of doing it yourself, learning how to mix these things, understanding what the ingredients are, and then having the right people who can actually apply them. And I mean, that's now in terms of coating, but also to build these walls. We face lots of challenges in terms of finding the right design mix, let's say for a compressed earth block, and then actually making sure that it is being maintained throughout the whole construction period. Moisture content is a typical thing, very difficult to get the moisture content right. I remember when we did the Renzo Piano project there, of course, they had a moisture meter and they constantly checked for the perfect moisture content in their mix. For us, we just, use somebody's feeling, and he touches with his hand and he makes sure that, it feels right. But that's, of course, not something a structural engineer is very excited about. So I think these are some of the challenges. There are very many. I could talk the whole evening.
Right.
One challenge we could help with, we could always send our paint to Uganda.
That's great. Yeah, you should set up a shop here, like a little agency.
Yeah, it sounds good.
We have some space in our studio. We could do that for you.
Mm-hmm. So the other question is, what do you think is the future of these innovative construction techniques in the Ugandan context?
If I can just answer that, I think the future is very, very bright. But not only in the Ugandan context. I think this applies to everywhere. But obviously right now it is a very small niche. You lead by example, you learn by doing, you communicate, you show, and then there will be more and more people who find this interesting. I think the idea of indoor health and of how do we want to live and how don't we want to live, I think that's getting more and more common. Maybe it's not so common yet in Uganda, but I think it is gaining more traction. And I think I'm never so worried about the quantity of something. I think you need to get the quality right, and you need to show what the benefits are. And then with time, you'll find that people actually are quite interested and start emulating.
Yeah, very much so. If I can just fill in from our own experience, I mean, we doing this now for over 25 years. And initially when we started, the saying was always, come on, Bernhard, you know how to make proper paints. Now you come with this green nonsense. You know, that was 25 years ago. Today, people come to us, want advice. There's very much a shift in perception of what is good for you, you know, like with all these organic trends and whatever else we had over the years. But I agree with Felix that the general perception of what is good for you has changed drastically. It is unfortunately in part also, again, cost driven, if I may say so, because we are still more on the expensive side. That goes for natural buildings, techniques and so forth. But we, for instance, just come off the wood conference, which took place a couple of weeks ago here in Cape Town. And the idea of timber building, which is also a natural way of building, has come huge, you know, like, I mean, they started that conference 12 years ago, I think it was, with about 20 people, and now they had over 600 delegates, predominantly architects, for mass timber buildings, and it was exciting to see how that shift has happened over the years. And the same for us. I mean, like I said, 25 years, probably concerned at least 15 years of educating people on what is good for them. But and the same will go for natural building techniques. And like Felix said, I think there is a very bright future ahead for all these techniques. Yes.
One thing I would add to, I would say the future is our Localworks' small contribution to the future is we're documenting as much of the research as we do, because one of the things we've found is that sometimes the information is lacking, especially here. You find people who are shocked that earth bricks can be tested, or that they have strength, or that you're able to determine the strength, who are shocked that bamboo is, you know, can be used and you can quantify the values or the parameters you need in order to design it. So we're slowly building a small materials library, and we hope we'll be able to share these things so that more people can do them. Basically, the more you know, the more you're able to do. Yeah.
Yeah.
I think that naturally goes into the next question, which is about relevant building codes and standards in Uganda that are being followed to ensure quality control. So are there any? And I think you've hinted on the fact that with every project, you're sort of creating a kind of library on your own of the things you're doing. So maybe to throw some more light on the part of the building codes and standards.
So so interestingly about Uganda, the code that we now use as the industry standard here is the European code, right? And the basis of this code is to adhere to the principles of material strength, material durability, and how you use the material. So it allows you to borrow from other codes from around the world. So for instance, in regard to earth, you find New Zealand has design codes, design standards, and these are the standards we use in designing our earth buildings. Timber, well, timber, you know that Eurocode has these same standards. Even the Uganda standard has these. So yeah, these are the standards we use. The standards are there.
Okay. There's a question from the first presentation from Daniel Sekama, who asks to share the pros and cons of breathable walls. I seem to recall Bernhard hinted on it as well, but maybe with regard to if there's something more you would like to say on that.
Well, actually, I think Philip really outlined it very nicely. I mean, and first pointing towards health benefits, you know, like that you try to maintain a beneficial humidity level in your house, which is not achieved by using cementitious surfaces. which dry out extremely quickly. They don't store moisture the same way, and certainly don't release moisture the same way as concrete does. I think further benefits apart from health is that we actually are using material that are locally available. I mean, Philip pointed that out a number of times, that don't need to be manufactured with huge energy input like cement unfortunately takes. And we can utilize materials that are literally found on site where that building is going up. You know, we can use the clay there, we can use various other things, potentially even timber that is on site. So I think overall, what I'm concerned at is that there are only pros for breathable walls, as far as I'm concerned.
So I'll add just one con. So anything that's breathable, it comes down to density, right? The more dense the material is, the heavier, the harder, the stronger. And you can see where this is going. You know, the more breathable, the less dense, it's lighter. So you find that to get considerable strength, you need more material. You need thicker walls. You find that rammed earth walls considerably thick. You find that earthbag walls considerably thick. You'll find that timber, very good in tension, compression, not so much, you know. So that's one of the cons, but the solution is to understand the material and understand how to use it in conjunction with other materials that give you the strength you need. Earth being good in compression, timber being good in tension, combining the two in unique ways that you can utilize the strength. That's the solution. Yeah.
Maybe to add one disadvantage, I mentioned it before briefly, that whole issue around scalability. So much of the techniques that we have been looking at are in situ techniques, and that's one of the the real attractive elements of it. You use the material from the site or very nearby the site, and you apply it sensibly. Obviously, scalability then becomes an issue. You can't easily, let's say, make stabilized soil blocks in a factory setting because they're not really transportable. They're very heavy and very brittle. That's one example. So I would say you also need quite a bit of knowledge, engineering knowledge, to make a material on site. Whereas if you buy a product somewhere in a hardware store, there are some experts who make this product for you, and you just buy it and you follow the rules of how to apply it. And of course, if you make your own material, you need somebody in your team who has that knowledge. So I think that's a key disadvantage of working in this way.
Yeah.
Right. He adds, contrast the experiential difference between a room whose walls have a good breathable score against one with a bad breathable score. So experientially, how would the two rooms compare?
This is a great question. I have to jump in there because I have two very good examples for that. One that I'm sure most of the Ugandan audience at least can relate to, and that is if you go into an old village building here that is normally built out of wattle and dope, and you can go in there, and honestly, it doesn't really matter whether the doors and windows, whether there are actually many windows, because very often there are hardly any windows there. And it doesn't really matter whether it's permanently ventilated or not. You enter there and there's just simply a fresh indoor climate in there. It feels cool and comfortable. I think that's something that many of you may know. The other thing is that everybody who is in construction, there's one key difference between a conventional building site and let's say an earth construction site. That's towards completion. When you enter in a normal building, for the first weeks or so, you have this very dry, cementitious smell everywhere. It takes ages for it to completely go, and of course, that smell is then very often mixed with the chemical smell of paint. when it's sort of last minute applied, etc. The amazing thing about buildings that are built out of earth or of breathable materials, but particularly earth, is that they are comfortable from day one. Even during construction, they're already incredibly comfortable. Anyone who's now going to the 32 degrees project will not really notice whether the project was completed a month ago or 6 months. You can just enter there and it is cool and comfortable and fresh.
Great. Ivan Ekonya asks, do you do model simulations with material specifications punched in just to gauge overall building energy performance requirements on a global level as opposed to just a single wall material tests? So I think this is more on the engineering side. Philip?
Yeah, it's more engineering, but it's also, I think, more mechanical engineering, basically to gauge mechanical ventilation, lighting, and things like that. One of the interesting things, there's a guy, he's a doctor at Makerere. I went to the same school as him. He's actually also Edson's friend. He's an electrical engineer. They've been making equipment and AI that tests the difference in climate in different locations, outside the building and inside the building. And I remember we thought to ourselves that this guy needs to give a local talk to talk about these things. So yeah, people are actually doing this. In terms of building energy performance, there are two stages. I would say the performance when the building is built in terms of how much energy you need to basically ventilate it, to light it. But there's also the energy used in building so making the concrete or the steel. And yeah, people do model this. We haven't yet modeled this at Localworks, but it is done. Our tests are usually strength and practicability.
Okay, and possibly if Ivan does it, I think we are open to, working with him or inviting him over to show us how that is done. The anonymous attendee once again asks about the cost effectiveness of breathing walls. So maybe our answer wasn't, he needs us to double down on that. Are they actually cost effective?
I sort of feel we've answered this. I think our answer is they are, if you look at the big picture.
Yes.
But if you just look at your wallet during construction time, then they tend to be more expensive.
Mm.
But also, always be clear that you need to compare like for like, in terms of durability, in terms of everything that goes into the considerations of which type of materials you're using. You need to make sure that you're comparing like for like, and then I feel over its lifetime, you will have a so-called cheaper product if you use natural materials.
Jesse,
if I may just slip in there quickly, my colleague just reminds me it was actually quite an interesting aspect at the Wood Conference where they put out prognosis of a building to last, let's say, 50 years. And what to do with those materials after 50 years. Will the original supplier, take them back, reuse? Amazing calculations that we never thought about it like a couple of years ago. But even the screws, metal components, everything that went into these timber buildings had to be almost given a justification what will happen once that building comes to the end of its life. If I think of a breathable wall or a wall that is made from local components, your lime, your earth, and whatever else finds into the wall, this damn thing, once it falls down, it goes back where it came from. There's even the steel, if you like, it also came from the soil. But I think it's a wonderful thing about an earth building, apart from all the benefits that we now reflected upon all the time, but we created something that nobody else needs to ever worry about it, should it eventually disappear or fall down or something. So when there's nothing dangerous to leave behind, and I think another nice benefit to have.
So Jesse asks, just for clarity, it may have been talked about at the start of the presentation by Felix. Are breathable walls a technology that is only viable in our climate, generally tropical? Would it pose a problem in colder climates to allow that breathability, especially in regard to regulating temperature?
If I may jump in, being originally from the Northern Hemisphere, if I look at the trends within natural building and certainly natural paint manufacture within Europe, they often prefer to have chalk or lime-based paints, or even clay plasters, and they painstakingly try to recreate that breathability, even at a small layer on top of originally concrete walls. I like to have this benefit of a regulated humidity within the building. So I think there is lots of benefit. Yeah.
The question is great that Jesse is asking, because I mentioned that in my intro. We have that, we are in that luxurious position that we don't need to think much about cooling and heating and all these things. Uganda has always got the same climate throughout the year, more or less. I think green architects in Europe face much bigger challenges. They need to prepare for winter. And they are now in a situation where building codes start prescribing how much energy a building must consume and must not consume, etc. And then there's this race to seal the building off as much as absolutely possible. And if you seal it off like a plastic bag, like a perfectly sealed envelope, then of course you now need to start bringing ventilation in, and you start actually mechanically ventilating normal houses. And people are not allowed to open their windows as much as they want, because then their energy calculation goes literally out of the window. So I think in that context, there are still very interesting developments. So for instance, I remember when we talked about straw, straw has fantastic properties in terms of insulation. And you can actually achieve those, zero energy standards that the European regulations now require by using unsealed, heavily insulated walls using straw earth, for instance. So I think there are ways there as well. So I would definitely answer his question that in the way that the whole issue of breathability applies anywhere where you construct. It doesn't matter. You just need to, of course, always design with your climate in mind.
Great. Etho Nekesa asks, how do these types of walls perform with storied buildings in terms of strength? So I guess that came from the case studies we showed. So how would it act on a storied building?
So the video was from Lwengo, and there the breathable wall is mostly infill, right? It's not the main structure. So that would perform very well with a storied building. If you could get a frame that is braced in other ways, you could actually even use the timber to brace it, then yeah, that would perform well. For going on to rammed earth, if you used it with a storied building, you have then to use a light deck, something lighter than opposed to your usual concrete slab. Yeah, because earth is not usually as strong as your other materials. But it has been done before. People have used earth to build storied buildings. Even stone can carry a suspended slab. Then you could always put something lighter on top as a roofing frame and whatnot.
Great. A follow-up from Ivan. He says, I have seen tools like Autodesk Insight, a plugin to Revit that can actually make the models he was talking about, the model simulations. So his question on model simulation was speaking to just how big Localworks has been able to go with this method of construction, because bigger buildings present more complex geometry and a need for energy audits. So I think it's more of a comment for us to, take on board. The anonymous attendee once again says he agrees with Philip's remark from earlier. Documentation of these materials and how they work would then be a good contribution to understand and experiment with more locally available materials. Understanding how these materials work would get architects in Uganda to go out of their way to achieve comfortable indoor environments. Is there some kind of a catalog on materials in the country? None that I know of, but maybe.
Not yet.
Not yet.
We're going to write it.
Yeah. And then the last question we have is from Andrew Lutwama, who asks, the termite builds earth tunnels off timber, perhaps using resins thereof for cohesion. And amazingly, the tunnels are robust to the climatic elements and are breathable, though brittle to human touch or excess force. Could there be a leaf borrowed from the termite? I think it's an interesting question for sure.
Yeah, I think we just need to analyze that termite spittle, how they stick all these particles together. And I think this is a rather well-researched subject. I actually never looked at it, but yes, I think what one can use, that was my favorite subject earlier, how to ventilate a big building from termites. They got amazing structures, and they are huge, at least by termite standards, and how well they are ventilated, and they got like the perfect climate all the time, no matter what temperatures are in or out. And they've certainly got breathable building materials. But yes, I think we can learn a lot. If I look at my biomimicry channel, that reflects every now and then on those building techniques as well. But yeah, no, it's certainly, I would say, yes, give termites a chance.
There's a question from Peter Mushoborozi. What's the difference in proficiency with paint colors? And I think this
Sorry, James, repeat that again.
What is the difference in proficiency with paint colors?
I'm not quite understanding what exactly he's after.
Yeah.
I think what he's asking is the ability to pigment these coatings that you have, Bernhard.
All right. Okay. I struggled a little bit with the word proficiency in that context, but the pigments that we use are predominantly iron oxides in various forms, especially if you look at African soils. I mean, they're generally a beautiful iron oxide red or yellows. We actually use these pigments. In all fairness, we hardly ever can use the naturally found pigments, because they unfortunately don't give us the consistency of color that unfortunately is required even from a natural paint manufacturer. I cannot this week deliver something that is maybe ochre red, and next week it's maybe not so ochre red. So and that's unfortunate if you deal with natural pigments, that there are huge variations within color. Generally, these iron oxides can very easily synthesize with very low energy input, and they will always give you consistent colors. Other colors are all mineral based, So yes, and we can, if you want to have a look at our website, we can do a huge spectrum of colors. Felix had the chance to have a look at it last year when we met at Haug. Yeah, now colors are generally not a problem. The colors that Philip showed earlier, you know, that little color scale they did on the one building, that is sort of the line of pigmentation that we also use, yes.
Maybe a quick one, Bernhard. You mentioned casein a few times in your presentation. Can you,
Yes.
I think not everybody in this audience knows exactly what this is. Where do you get it from? How is it made?
Okay, the casein or casein starts with the cow. And the cow produces milk, and the protein in the milk is actually the casein, and that's where käse and cheese and all that word results from. It's actually the casein that makes these things. We can coagulate that protein out of milk, and some people enjoy it then as sour milk, you know, when it's still not dried up. But the essence of the milk is the milk protein, and that is exactly what you either make cheese from, or you dry it up and modify it slightly to make caseinates and so forth. And these are wonderful polymers that nature offers, or in that case, the cow offers. And that can be used, first and foremost, we use it as a emulsifier to bring the oils into a water phase. You know, all our war paints are water-based. And but also that these caseins form wonderful bonds with lime, especially lime. It's actually the wall that doesn't contain lime, the casein is not so happy about. I mean, a super strong bond. That's why we incorporate that into our wall paint to facilitate that hard bond with the substrate. And it's breathable.
Brilliant.
All right. I think we've actually come to the end of this edition of our Local Talks. I'm going to ask each of the speakers to give their parting shot, starting with Philip.
I was not prepared for this.
Me not either, James, really.
I would say there's something Felix said when someone kept asking about cost, and what is the cost of your health to you? I think that should be something we think about. I think breathable walls are something everyone should consider and should take their local engineer to task about when they're building. Yeah.
Great. Bernhard?
Yeah, I can join in there. I mean, for the love of health, your own health and the environment, give these breathable walls a chance, or the whole natural building story is something not to be snuffed at. I think we established that it does have a green future, and I firmly believe, and just as I better do, because I'm doing it for 25 years now, that these green developments really, first of all, come from our hearts, but also are so valuable. And if you think what strides we made, even when I looked at that video, when I went to the first green building sites, I saw people trampling cow dung into clay, and they had it in a tarpaulin, and we all stomped, and then it was more like a rain dance rather than trying to create a building. But I mean, it sort of put the group together. It was actually a wonderful experience, and now I see that you got pre-forms, and it's, I mean, even that came a long way, you know. And now green is here to stay, and give the walls a chance.
Right. Thank you. Felix was not officially a speaker, but since he's here, Felix, you have something as a parting shot?
Well, I've learned a lot, and I'm really grateful to both Philip and Bernhard. It worked really well the way these two presentations have worked together. I feel, Philip looking more at the walling material and the substrate, and then Bernhard talking about the coatings. There's of course lots of questions. The good thing is both of them are available on email and can be asked those questions. I think they will also both share their presentations. Really just the idea I just got when I listened to Bernhard talking about casein, I think this is of course not a product that you can get in Uganda easily, so we should just make it ourselves. This is Uganda has lots of cows and lots of dairy production. It should be very, very easy to make this stuff and to mix our own paint until ProNature sets up a shop in Kampala.
Yeah, I'm always available for looking at locations for our factory in Uganda, obviously.
Right.
But I would love to come. Maybe we do something like this, like a Ugandan seminar on how to make paints, and then yeah. But it's actually much easier buying it straight from us, I must say.
All right. Thank you all. Thank you to the viewers that have been able to tune in. A big thank you to all our speakers and panelists. This content is going to be shared on our YouTube channel. Endeavor to subscribe also to our newsletter for news about future local talks, and feel free to get in touch, and with feedback, further questions, we would be happy to respond to those. So thank you and see you next time. Bye.
Thank you, James.
Bye.
Cheers.
Thank you.
Cheers, everyone. Ciao.
Yeah.